Many alkene reactions that we're going to be studying are electrophilic additions. So we're going to have additions to the double bond, meaning we're adding here across the bond. So we need to remember that what are nucleophiles and electrophiles. And so electrophiles are electron deficient species. So we're going to represent it like that. So electron deficient, but they can also be somewhat delta positive. We're going to see examples of that in this reaction. Now, nucleophiles, on the other hand, are electron rich. Let's say that. And here we have a number of examples. This is one nucleophile, but this is another nucleophile that has charge. And we also have pi electrons. And so that's what we have here. So now let's get study one reaction, starting to study reactions of alkenes. So one important reaction of alkene is the hydrohalogenation. So in the hydrohalogenation, then you will have hydrochloric, hydrobromine, so on. And what we will have here is then the electron-rich species is here. Electron-rich is the double bond. So pi electrons are going to go and attack here, and you're going to get the following. Since I don't have room, I'm going to erase what I have here on the right-hand side. So what is resulting from that? The result is that I'm adding an H and I am creating an intermediate. I'm going to add an H here using those electrons, right, making that new bond, and I am forming an intermediate called a carbocation. Then we will have the first step we're going to call a proton transfer. Proton transfer. In the second step, we will have the attack by the nucleophile, which in this case is the halide. And now we are forming the following, right? So end result is that we have added H and H here and X say across the double bond. So, but let's do another example of that. Let's say that I have this alkene, this is cyclohexene, and that I want to do same thing. Let's say that I'm now working with hydrobromic acid. So when I do that, and I'm going to add a substituent here. I think it makes it more interesting. Now, let's see what are my options. Okay, same thing we're going to be doing. Let's attack with the pi electrons and get the proton. So what are my options here? If I, using those pi electrons, attach the, so I'm making the bond carbon-hydrogen at this carbon, I will be creating a positive charge in the carbon above. In other words, let's just write it down. I add the H here, and this carbon is going to be your carbocation. And now that is one way. In that carbocation, notice that at this carbon you have 1, 2, 3 substituents, so that's tertiary. And if we did the opposite, I'm just doing that again, right? If we did the opposite, if we had added the hydrogen on the top carbon, then the positive would be on the other end. So what I want you to see is the difference. If we had proposed that, that is a secondary carbocation, which is less stable. So typically what we have here is that this reaction happens in such a way that we form that's the major, say, product. And that is, say, regioselective. In other words, you are more selected to the position that is going to produce the more stable carbon cation. So the hydrogen will be added to the least substituted carbon, because that way we form this carbon cation. What happens afterwards, and I'm going to erase this one, that's not my most important product, my major product. Again, we said it was regioselective. Now, the next step, first step was proton transfer, similar to what we did before, proton transfer. In the second step, we will have a nucleophilic attack. And my nucleophile here is bromide. And now I am going to have that attack over to the carbon cation and have my final product will have a metal and a bromine here. And not the, not the other product with the bromine in a different position. So yeah, the reaction, then you're going to, when you do the hydrohalogenation, the hydrogen is added to the least substituted carbon in the other group at the more substituted carbon. That regioselectivity we call Markovnikov. And that is after the chemists that study those reactions. So this addition is Markovnikov, meaning that it will produce the more stable carbon cation. We will do more examples on that.